So today we are learning displacement and velocity for AP Physics. And this is part of Unit 1, which is Kinematics. So now, the first thing you need to know is the difference between vectors and scalars. So a vector quantity is something that has direction and magnitude. While a scalar only has a magnitude, so it's only a value. And it's important to remember this because an example of a vector would be something like velocity, while an example of a scalar would be speed. And I'm just going in with all of these videos with the assumption that you already know how vectors work in a plane very well and in one dimension. So if we have this vector here and it's pointing like this, if you know what theta is, you should be able to know what its vertical and its horizontal components are. So given we know that this is some sort of vector, you should be able to find this component and this component using sine and cosine. So other than that, there aren't really any other things you need to know to get into it. But I should also probably mention that some examples of a scalar would probably be like energy. We'll get into this in Unit 4. And like velocity could also be like acceleration. Or it could also be like displacement. So yeah, let's get into it. So to start off, displacement is basically just the distance from the starting point. So it's just change in x, if x is our position. And that's why if I run around in a circle and I start at the same spot, the displacement is 0. Because the difference between my starting and ending position was 0. So it's important to note the displacement is not distance traveled. And that's really important to remember. Okay, now moving on, we have velocity. And let's write down our definition. Velocity is just a change in position over a change in time. And this is in meters per second. And I should mention displacement should be in meters when you're doing all these equations. And velocity is not speed. Speed is one part of velocity. Speed is the magnitude of velocity. But we don't have any direction in speed. So that's just important to note as well. Anyway, so moving on. We should probably go over some graphs. Like this, like that. So if you have a position over time graph, and it looks like this, and then like let's say you go like that and then like that, the velocity is equal to the slope. So equals slope of position versus time. So we'll notice that our velocity here and here is actually the same along these two intervals from here to here and from here to here. It's 1, right? If we're going by units. And then here it's 0 because slope is 0, so velocity is 0. And it should be pretty obvious if velocity increases, slope increases as well, and vice versa. So if something is like steeper like this, obviously there's a higher velocity. Now, there's another graph that you should probably know, which is a velocity versus time graph. So we have v of t versus t. And be sure to know that this is in meters per second and this is in seconds. And remember, if we have velocity is equal to distance over time, that means velocity times time must be distance, right? So this is important. Let's say I started at 3 meters per second, and then for the next part I go at 2 meters, and then in the next part I go to 4 meters. So if I draw some rectangles here, what do we notice? So the area of this rectangle is what? It's going to be 6, right? If assuming units, and assuming single units along the x-axis. I should probably write that. This is 6, and then this is 1, 2, 3. This is a 4. Yeah. And I'll talk about the units in a second, but let's just write 6 there. And then this will be 4, and this will be 8. But notice that we're multiplying this length, which is in meters per second, over a height, which is in seconds. So what this tells us is that these are actually in meters, because if you remember your dimensional analysis, meters times meters over seconds times meter of seconds, the seconds cancel. So it turns out to be distance, a measurement of distance. And if we notice, if we add this all up, we actually get 18 meters. But the thing about this 18 meters is this is the total distance traveled between 0 and 6 seconds. And if you've taken a calculus course, what basically I'm saying in a fancy way is the area under the curve of a velocity versus time function, area under it, so the integral sign, right? If you do that, is equal to distance traveled. And that is basically the most important thing when looking at these types of graphs. Other than that, let's find how to do average speed. So average speed is slightly different than velocity because it's the total. So let me just say speed average is equal to the total distance over total time. So let's say Sally runs 15 meters in 30 seconds, which is really slow, or let's just say 5 seconds. Find average speed. And this should be pretty obvious. It's just going to be total distance, 15 meters over 5 seconds equals 3 meters per second. And that is her average speed from t equals 0 to t equals 5. Now notice, if I asked you, find her speed when she's 2 seconds into the run, we don't have enough information for that. We have no clue. So the only way to find that is if we're given that it's constant speed the entire time, or if we're given a graph. So if I do it like this, and let's say this is her velocity, right? Over some period of time, or let's just say this is her velocity over 5 seconds, and she is somehow able to run 50 meters. So what that tells us is that the area under this curve is going to be 15 meters, because that was what we were told, right? Area under the curve of a velocity versus time function is equal to the total distance traveled. So if I wanted to find out, well, what's her speed at 2 seconds, I would have to find the slope here. And unfortunately, the only way we're able to do that is with calculus. So in AP Physics 1, you don't need to worry about that. But that would just be the way. So like if it was a more simple graph to find out, if it was something like this and then it was like that, and that somehow still added up to 15, then you could just tell that her speed at the 2 second mark was 1 meters per second. All right. So that's all the notes we're going to do. So continuing, we're going to do some problems. All right, so for the first question, calculate John's average speed if he runs 140 meters in 5 seconds. This one's pretty easy, so why don't you guys pause the video, just do the quick calculation on your own, and I'm just going to solve the problem right now. So this is obviously going to be our V average formula is equal to total. So that's the total distance over total time. And this just gives us a nice and easy 28 meters per second. All right, moving on to the next problem. So the second problem I'm going to do is going to be Anne and Becky run on a straight track. And I'll return once I write this question. So if Anne starts 10 meters ahead of Becky and runs at a constant 3 meters per second, while Becky runs at a constant 4 meters per second, if they start at the same time, when will Becky overtake Anne? So it's usually nice to just draw it out. And then we'll have Anne and Becky 10 meters apart. So Anne is over here, and she's running this way at 3 meters per second. And we have Becky over here running at 4 meters per second. And basically, there's this 10-meter gap between them. So we have this 10-meter gap. So what we need to first do is model their motion with some equations. So let's take Becky's starting point to be 0 and Anne's to be plus 10. So that means Anne's position is equal to 4 meters per second times t, while Anne's position is going to be 3 meters per second times t plus 10. And we want to find the time when they end up at the same position, so we'll set these two equal to each other. So 3 meters per second times t plus 10. And notice how we can actually subtract this from this side. So this becomes 1 meters per second, and we should actually add the meters, times t is equal to 10 meters. And if you just do the dividing of the units, we get t is equal to 10 seconds. And that is our answer. And that's all you really need to know for these basic velocity problems. And I'll see you next time, where we'll be talking about acceleration.